Autodesk Offline Robot Programming Made Easy. Hi, I'm John Caligiuri, Director of Sales from DSI. I'll be joined later by Mike Caligiuri, our Director of Engineering, to talk about Autodesk Offline Robot Programming Solutions, applications for robotic milling, challenges, and techniques. We're going to do some introductions for those of you who may not be familiar with DSI, a quick overview of the Autodesk Make portfolio of manufacturing technology. We'll do an introduction to robot and go over some basic terminology for those who may not be as familiar with robotic milling. Then we'll discuss the common applications that robots are well suited for in the machine shop, as well as a technical demonstration of Autodesk Power Mill Robot Interface. So first, DSI is Design and Software International. We're a Make specialized Autodesk Gold partner in USA and Canada with engineering and sales offices throughout North America. We have been selling, supporting, and developing and customizing CAD, CAM, additive, and metrology software in North America for over 30 years. Autodesk is a company that needs little introduction, although most people associate Autodesk with the AutoCAD company. And while that is absolutely true, in recent history, Autodesk have made major investments north of $1 billion to acquire industry-leading advanced manufacturing technology. The result of this acquisition and organic growth is the most complete advanced manufacturing portfolio of software solutions on the market, with everything from design exploration technologies like generative design, plastic injection molding simulation, a host of subtractive programming tools, additive path planing tools, and inspection and fabrication solutions. Also, the platform of the future, Fusion 360, these round out the portfolio of manufacturing solutions at Autodesk. These are backed up by a team of over 600 software developers working on design and manufacturing technology, and 6 state-of-the-art manufacturing innovation centers throughout the globe that prove as a proving ground for our solutions, as well as a space to collaborate with customers. So let's get into it. Today we're talking about robotic CNC milling and other CNC machining operations. So what is a robot? What are we talking about? This may be what comes to your mind when you hear robot. What we're talking about today are industrial CNC robots. The most prevalent would be KUKA, ABB, Fanuc, Motoman, Hyundai, so on. These come in a variety of arrangements, hereby referred to as a cell, and can be used for all sorts of manufacturing tasks. The advantages that robots provide, why a robot might be well suited for an application, are related to they're very scalable for large parts. There's a lot of freedom of movement. Robots are extremely flexible. Highly adaptable. As you'll see in the next slide, we can arrange CNC robots in a number of different ways to gain different benefits. They're more mobile than a traditional CNC manufacturing center, and they're quite happy to work in hostile work environments. This is also why you see a lot of robotic assisted tasks or robotics replacing tasks that human beings might have done traditionally in a composite dust environment or a stone dust where there's respiratory concerns, radiation in a nuclear facility, heat in a foundry, and so on. So robots can replace human beings in certain cases where the work environment is very hostile. Some things to consider when choosing a robotic application that might be seen as disadvantages would be limited accuracy of the robot itself in comparison to a CNC machine tool. There's an issue of singularities, which we'll define and discuss, and material limitations. The robot only has so much rigidity in a milling operation. You're not going to have a lot of success machining tool steel and hard materials. So what does an industrial robot cell look like? These are just some examples of what it might look like. So the most common is going to be this KUKA, the spindle on robot, with the robot addressing a workpiece, either on a stationary fixture or on the ground. Also common would be the Motoman cell, where we have a 1 or 2 axis external positioner for the robot to address the workpiece. 6-axis robot plus 2-axis positioner with a tilt-rotate table would be referred to as an 8-axis robot cell. The ABB cell listed has a linear track, giving the robot the opportunity to address a large stationary part. And the FNUC has a situation with a stationary milling tool where the part would actually be manipulated by the robot about the milling tool. An example of this might be a robot picking up parts as they come down a conveyor and deburring them on a stationary tool. Before we go any further, a bit of free advice from DSI. A robot plus a machining spindle does not equal robotic milling success. There are many, many things to consider when constructing a cell or implementing a robot for machining purposes. If you do not have a background in this, please find a reputable robot integrator who does to assist. DSI have a network of preferred partners that we use for these applications. We would be happy to make an introduction. Here are some applications that we've had great success with Power Mill Robot. Foam sculpting with a milling tool, foundry sand mold milling, plastic or composite part trimming, drilling in all sorts of materials, cutting, whether it's with a hot wire, which we'll see in a little bit, roughing foam, or plasma cutting with a plasma torch, or an indexable knife. Some other applications are welding or additive manufacturing, such as wire arc additive manufacturing, laser powder or laser wire additive manufacturing, and polymer extrusion additive. Grinding, polishing, linishing, and measurement are also possible. Before we get into the technical presentation, most of our customers have a high degree of comfort and familiarity with CNC machine platforms. So let's relate some robot terms to CNC terms to make sure we're all on the same page heading into the demonstration. Robots that we'll be discussing are 6-axis or more if there are external axes like rails, rotary tables, and so forth. So 6-axis robot should be a direct correlation to a 3 or a 5-axis machine tool. We're referring to the rotary axes of the robot. Where a CNC machine would refer to a G54 work offset as a part origin work plane, robots would call that a base or a base work plane. Tool length on a CNC machine is referred to as a tool plane or a tool work plane on the robot side. Then a couple of differences. We need to worry about robot configurations and singularities, which we'll define in the robot world, where we don't in CNC machine world. Also, for large 3D milling toolpaths, it is a concern with some robots that there's very limited memory available compared to CNC control with a large amount of memory and high-speed look ahead. Robots are very accurate in general, but when we talk about machining high accuracy parts like you might on a CNC mill, where we're holding, maybe 1/1000th of an inch tolerance or less, or tenths, you won't be doing that on a CNC robot. So just a few more. Joint angle refers to one of the 6-axis rotary positions of the robot. So is the position of one of the rotaries. Joint position is the position of the robot itself as defined by all of the joint angles. Home position is a predefined set of joint angles that we would refer to as the home of the robot. Singularity, what we've been talking about avoiding, is a position of the robot where there are multiple solutions for that angle, multiple possibilities for the next move. So usually when this happens, the robot halts and can't carry forward. It's like a machine fault. There are different kinds of singularities possible. An elbow singularity, where the second, third, and fifth axes are aligned. The alignment singularity is referring to axes 1 and 6. And a risk singularity is 4 and 6. So you can see clearly on the screen where these come into play. We are now going to jump to Mike, and he's going to run us through a couple different robotic machining operations done inside Autodesk Power Mill Robot.
Okay, let's get started with the technical portion of the presentation. This is the part we're going to program in Power Mill today. And the one thing I'd like to point out is with Power Mill, the nice thing is that we can not only work with surface and solid data, but we can also program things that are already STL or mesh data. So if I right click on top of this, I can go to properties. And what I can see is that this is actually a triangle model. So we can actually work with a mixed environment of data as well. So one thing we've done is in the CAD portion of the product, we've actually modeled up a fixture, which is just a little post to be able to hold it. In this case, this is actually surface data. So you can see how we can work with a variety of different types of CAD models and origins. For a lot of artistic machining that is done on robot type cells, usually these are artistic things in nature, a lot of times cartoon characters or architectural pieces that have either like a theme or a cartoonish type effect to it. A lot of times these are created in products like Autodesk Maya or 3D Studio Max, where the data itself is actually a triangle model. There is no CAD or solid model for that. So it's important to be able to work with a variety of different CAD inputs and also different types of geometries. So if I go ahead and turn on the robot cell we're going to be working with today, this is actually going to be a KUKA cell. And you can see here, this actually has what's commonly referred to as an external axis. Now, the way that the robot is set up right now, it actually has what's referred to as a hot wire system on it. And these are used to go through and actually rough out usually a cube stock and remove large portions of it by using a hot wire to be able to cut through that. So the first part of the technical presentation is going to be showing how we can program a hot wire and also leveraging some automation. Design and Software has been working with a lot of robot integrators over a long period of time. So we've developed a lot of automation tools that we provide to our customers that help automate the programming of robots that do a lot of commonality, like either hot wire systems, or in a lot of cases, people like to do what we commonly refer to as an apple peeler style rough. Today, we're going to concentrate on the hot wire because it's probably a little bit more of a sophisticated programming method, and I think it kind of highlights some of the automation a little bit better. Okay, so I'm going to go ahead and turn off the robot for now, and just kind of let's focus in on the part itself. So one of the items that we provide to our customers is what we refer to as a DSI Power Pack. And in here is a variety of different tools and functions that are used. Some of these can be used specifically for milling, some of them are specific for robot. In our case, we have a few things here we're going to concentrate on that are underneath the robotics section. And specifically, we're going to concentrate on the hot wire rough. If we select this, it's going to basically first ask us to select a work plane that is the bottom of where we're going to have the hot wire stop. I don't want to bring the hot wire all the way down to the bottom of this because it's effectively going to drag the table. So I'm going to bring it down to a point, probably to the bottom of this cone area, and just leave the rest of that material part of the square base. So we're going to go into the work planes and just create a work plane in PowerMill, just using standard PowerMill work plane creation tools. I'm just going to move that up 100 millimeters. We are doing this in metric. And I'm just going to accept that. We're going to resume the automation. At this point, the automation is going to start prompting me for a couple other inputs. Which methodology do I want to do the hot wire? We've kind of created two standard ones and then also one where you can choose your rotation. The most common one is 0, 180, 90, 270. So basically hot wiring it along all four sides. So I'm going to accept that. How much material do I want to leave after the hot wire to basically finish machine? I'm going to say 12 millimeters in this case. Do I want to alternate directions? So what it's asking here is, if I start the hot wire at the top and then hot wire to the bottom, on the next pass, do I want to go from the bottom and go up? Or do I want to have every pass start from the top and go down, or maybe from the bottom and go up? It just kind of depends on what you want. I prefer to do the alternating directions. It makes it a little easier to kind of keep the robot in a controlled manner as I transition from one hot wire program to the next. Then the final thing that we're going to do, which is really kind of a nice programming tool, is do we want to simulate the cut stock after the hot wire with a stock model? And yes, I do. So now the automation is going to kick back. So instead of having to go through all these gyrations and programming and clicks and, quite honestly, learning curve to be able to understand how to do this, we can just let the macro and the automation take over. So for one, it's saving me a lot of learning curve to be able to program this hot wire system very easily. For two, it's very easy to train part-time users or people that don't necessarily program the robot all the time. The other thing that it allows me to do is really save time. So besides the fact of not having to learn how to go through all this stuff manually, at the end of the day, what we have here is all the toolpaths are now created and calculated. And at this point, we could just accept the dialog box. Here. All right, so the result we see on the screen now is the stock model that we chose to have the automation create. The usefulness of this is we can leverage the stock model functionality that's inside of PowerMill, and we can see the results of what the stock would look like after the hot wire process has been completed. We can also come in here and look at the initial block form, and we can see that there's the block that we started with, and then we can visualize exactly what the block looked like after each process and step of the hot wire. So we could finally get to each of these things. So it's nice to be able to go back through and look. Not only can we use this as a visualization tool, the nice thing is as well as we can reference this as a starting condition of stock for another toolpath. So if we felt like we needed to come in and do more roughing operations, instead of using the original block form, it would understand that this material's already been removed. If I come to my stock model area as well, I can also change the appearance over to a wireframe. And what you can see is that inside of there is actually our part, the original part with the 12 millimeters of extra stock that we gave it. I'm going to go ahead and turn this off for now because I don't really need to see that anymore. And I want to just visualize this with just the part model on. Underneath the toolpath area, I can see that here's all the different toolpaths that we created underneath the folder called Hot Wire. So the automation went ahead and organized these things into a directory for us, as well as rename the toolpaths so we understand which orientation they're for. What I want to do is look at this with the robot cell turned on. And to control the robot cell a little bit better, I'm going to use the robot plugin. So we're going to turn the plugin interface on as well. So by doing so, we can now see the whole robot cell. I'm going to kind of keep zoomed in here around the part and go to my simulation speed and just turn this, make sure it's down to a nice comfortable level, and go ahead and play on this. And it's going to allow me to go ahead and simulate this thing from beginning to end. So I can see exactly what's happening with the actual hot wire itself. It's a little easier to kind of see what's happening there. As I'm looking at that, I'm like, okay, everything looks nice and controlled and smooth. One thing I'll probably want to do is open up the robot control so I can see the actual axis positions of each of these. I'm going to go and rewind that again so we can go from the beginning, and you can see kind of the total robot posture as it's moving through, which I think is also important is just noticing the motion of the robot itself. So nice, smooth, easy motion through the whole process, as well as the transition and connection moves. So the nice thing is the way PowerMill Robot works is we're actually recording the robot motions that you see on the screen, and that ultimately is what becomes the robot file that we post-process. So if we're happy with that, we can go down to our robot program and go ahead and write the robot NC program. This will actually output the program, creating the main routines for our KUKA, as well as the cutting sections of the KUKA as well. There's all the cutting coordinates in here, as well as, if we come back and take a look, in the main areas is here, just the same, and it creates all the different calls to be able to call all the proper subs. So now that the part's roughed out, what I want to do is go ahead and turn off the robot as we have it now. And I'm going to come down here to the bottom and just clear the trace, which just clears some of the robot connection moves for the roughing. Kind of collapse some of the different bits and pieces we have, including collapsing the robot interface itself. This allows me to kind of focus more squarely on the part machining itself. Let me just go ahead and deactivate this work plane. And that way we can look at just the part by itself. So let's begin with the finishing operations. First thing is we're going to go into our tool database and try to choose a tool that is typical of what we might use for machining foam. We've created a generic foam tool database that we can use. In this case, we're probably going to just grab a 1/2-inch ball nose tool. As you can see, the difference with kind of typical foam cutting tools is that they have much longer flute lengths typically. So let's go and create that tool. That'll add it to our tool list here. From here, we go and select which Toolpath strategy we wish to use. Although PowerMill has a lot of different ones in here for doing area clearance or roughing, curve machining to machining curves, feature machining, and as well as just a host of finishing strategies. Pretty much all these strategies as well can all be multi-axis, or it can be positional 3+2 for a robot. So we kind of don't really distinguish the difference between these. There's also things for like drilling and some dedicated things for like machining ports and some other things that are probably a little bit non-typical for robotic application, but either way, you have all those available to you. We're going to go down and look at our robotic finishing, and these are some very typical strategies that we provide that are typical of how you would finish machine something on a robot. And one of those is something we call spherical finishing. So we're going to go select that, and what we're going to need to do is go ahead and set a center point to where our spherical finish is going to emanate from. In this case, we're going to use a value of about 350 millimeters, which is a point roughly in the middle of where the head is on this part. We're going to go down to our rapid move areas and also calculate a safe clearance value. And we can display that. We can see that everything outside of this red area is going to be considered safe. The other thing we're going to want to do is specify our tool axis. So underneath our tool axis, we typically are going to use it towards point. Now again, we're going to go need to set a value specific to this part. Again, we're probably going to use the same value of 350 millimeters. So the tool's always pointing towards the center of the head. From here, if I take a look, I'm going to go ahead and preview this toolpath. And what I see is I'm projecting outwards from the toolpath. I want to project this inwards. So if I go ahead and preview that, now I can see that we're actually projecting down on top of the part. And from here, we could go ahead and just hit calculate. PowerMill is also multi-threaded. It's 64-bit. So generally speaking, the toolpath calculations are going to be quite fast. So there's the final result of that. So if we take a look at this toolpath, we can go ahead and simulate that from start. Without attaching it to the robot, we'll just go ahead and play this. You can kind of see exactly what the toolpath is actually going to do. So this is kind of why we call it a spherical finish. I can speed that up, and you can see what's happening here. Of course, we can give it a tighter step over if we like, but this might be just the first cut of many in order to finish this part off. Okay, good enough for now. I'm going to retract that back to the beginning. And what we want to do now is talk about loading in our robot cell. So we're going to go back to our view command, and let's go and bring up the robot interface again. And this time we're going to look back at our robot cell. And instead of getting the robot with a hot wire, we're now going to load the robot without the hot wire. Now we have the robot loaded in with the spindle attachment in place at the end effector. So from here, what we can do is go ahead and activate the toolpath that we want to simulate. We're going to go down to our robot control. And first thing is we're going to home the robot, attach the toolpath to the start. And then we can actually simulate the same process now with the robot in motion, which kind of has a little bit more impact as far as what's going to happen here. All right. I'm going to go and stop the simulation for now. I don't want to spend the rest of the time here watching simulations. And let's move forward a little bit further into the finishing process. One of the things you'll see is that a lot of times we have areas that have a lot of detail, like maybe around the mouth here, around the eyes. And what I want to do is kind of concentrate more on how will we go about adding some additional finishing passes just to these areas here. So let's go ahead and just turn off the robot cell for now. So I'm going to go back to my robot cell, and we're going to turn that KUKA robot off. We're going to go ahead and turn off the robot interface as well. And let's just come into a view that probably makes a little bit more sense. So we're just going to kind of look on the part kind of more just towards the front using the view cube here at the top. And we're going to kind of concentrate right around the mouth area. I'm going to go ahead and turn off the toolpath as well for the one that we already created, just to kind of clear the screen here a little bit. I'm going to go back to my home screen, and I'm going to create a work plane that's down here around where I want to kind of work. Right in that area there. I'm going to go to that work plane and just activate it. And we're going to use the work plane editor now in order to modify that work plane. And one of the things I want to do is go ahead and align that work plane to my current view. So now I can see that the Z-axis is pointing exactly the way that I was looking at it. Now, one of the things I like to do is I'm going to go and reposition that. I'm just going to move that up, I don't know, maybe 120 millimeters, something like that. Doesn't really matter. I just want to get it up out of there. And I can just kind of visualize where that's going to be at. Go ahead and accept that. And then I want to go ahead and take a look at that down the top view of that. So right around that same area, now what I want to do is create a boundary and isolate just the mouth region and be able to do a different toolpath just inside of that area, either to get more detail or just to clean up that result. So to do that, we're going to use our boundary tools. So underneath the boundary, we're just going to go right into our curve editor and tell it that I want to sketch a curve. So as we're sketching this thing out as well, the one thing to keep in mind is that this is just an approximation of where we're going to actually do the next toolpath. It doesn't need to be exact to the shape. It's just the area that you want to isolate to add another machining pass to. And even once that's completed, what we could do is come in here within that toolpath and modify that around by moving these points. You can control the tangency handles and kind of adjust the spline here a little bit just so it looks a little bit more fluid maybe to the shape. So whatever we kind of want on that. So if we're otherwise happy with that, that looks pretty good. We can then just go and accept that boundary. And then at this point, what we're going to do now is go and add in another toolpath, another finishing operation from our list. We're going to go back to the Home tab. Let's go and we're going to go into our toolpaths. In this case, we're going to select an offset strategy. So inside of here, we're going to go to our limit area and just specify the boundary we just created as our limit that we want to contain the toolpath within. We're going to go to our settings, and we might change the tolerance, maybe make this a little bit more accurate, perhaps. Give it a finer step over, maybe 1 millimeter step over. And then we can just go and calculate that. So when we get this done, you can see now there's a very easy way to come in here and actually isolate certain regions within the part and try to get a better finish or a clearer finish. You can also see we're kind of retracting in some areas right here. We're leading in, leading off appropriately. What we may elect to do is to go back into that as well. Go into the settings. With anything, we can recycle it and make a decision change and say, you know what, maybe we actually want to do a spiraling operation instead. So we go through and calculate that as well. Now we have a much cleaner result that's a little bit more appropriate to that area. So one of the common questions is that we have something that has a really detailed area. How can we go back in there, maybe even with a smaller tool, and actually clean up that area? As you can see, it's quite simple. We can just sketch a boundary and then apply a different strategy or different technique in that area.